Hi, it's been a while since my latest video, and this time I decided to stray a bit from my usual videos about games onto a video about making a compiler. This video was inspired by one of my college courses and the work I've managed to get done for that. I'm gonna be condensing the work of a full semester in a single video, so I won't go over everything in the greatest of details and remind me some stuff a mere college student misunderstood or has difficulty explaining, but I'll do my best to show you something interesting. Before making the compiler, we're going to need a programming language to compile, so I'm going to be creating one of my own. To describe the rules of said programming language, I'm going to use EBNF. EBNF, or Extended Backus Naur form, represents a way to use notations to describe a formal language, so they achieve something similar to regular expressions in a way. Here is an example describing an integer. We have digit, sign, and integer, which are called non-terminal symbols, and the rest in quotes are called terminal symbols. We can see that a digit can be 0 or 1 or any of the digits. The vertical bar means or. Sign can be either plus or minus, and an integer is formed of a sign in brackets. That means the sign is optional. Not all integers have a sign, at least a digit, and then in braces, uh, the braces mean that the digit can be repeated any number of times. And here is the rules of the programming language described using EBNF. The program has similar syntax to, so I'm gonna do similar syntax to C++. The program, besides the C++ syntax stuff, main and braces and parentheses, is formed of an instruction list. An instruction list can be either an instruction or an instruction followed by the rest of the instruction list. An instruction can be a declaration, assignment, control, loop, input, output, and you can see for each of these have their own rules. ID means identifier, so that's a variable name, while const is a constant, so a number or something similar. You can pause the video to take a detailed look at everything. Next up, a bit of info on formal languages, which I've mentioned before. These represent a collection of words or elements that adhere to a set of rules. I highly suggest researching more on your own, because I'll only give an example. So for this language, which basically represents a word that has any number of A's greater than 0 and ends with a C, we have these words that are part of the language, and these words, for example, that are not part of the language. Now I'll talk a bit about the stages of compiling. First, there is lexical analysis. In this stage, we take the source code and we generate a stream of tokens. When I speak about tokens, I refer to keywords. We have int, main, if, else, identifiers, variable names, constants, 5, 2.3, operators, separators, and everything. These are called tokens. Then syntax analysis. This stage takes the token stream and checks if the source code matches the grammar of the programming language. What the grammar means will be explained later, but it really refers to the rules of the programming language. There is then semantic analysis, which does more error checking, but we will not focus on this. And intermediate code generation, optimization, code generation. For now, we'll focus only on code generation. We'll skip the intermediate and optimization parts. But I might come back to this project later and also explain these. Also, if you're curious about uh, more on compilers, there's this great book. I will leave its name in the description. Let's get into the implementation. I'm going to be using Java. First, I'll define an enum for the possible token categories, an enum for the possible token types, a token class which contains all this information, and the token utils class which has a map which attributes to every token a unique code, as well as some helper functions that I'm going to use later. Now let's get into the Lexer, lexical analyzer. We're going to tokenize the input code. We're going to do it token by token. We have a function that tries to extract for every token category, and also some special functions for identifier constants. This function that extracts from categories uses some helper functions from token utils, and for now, extracting identifiers and constants returns null because we're going to have to do something different for those. To be able to extract identifiers or constants, we're going to need regular expressions, and something that can extract regular expression is a finite state machine or a finite automaton. A finite state machine is a mathematical model used to recognize patterns in an input sequence, meaning to check if an input matches a regular expression or a formal language. There are two variations, deterministic and deterministic. We'll focus only on deterministic. Here is an example of how a finite state machine or finite automaton looks like in its graph form. These are states, the circular states, and the states with two circles in them is that they are final states, so the processing an input can stop there. If we want to check the number 12, for example, if it's an integer, first we go on this branch, we process the 1, we are left with a 2, we reach the second state, and here we can process the 2, we're left with nothing, we're in a final state, so the sequence 12 is accepted, that's an integer. But if we want to check, let's say, ABC, we from the starting state Q0, we have nowhere to go with A, so the sequence is not accepted. For the implementation, we have a class with a list of states, the symbol alphabet, a map of transitions, and some information about the initial state and final states, and a function to add a transition. Some functions to check if a sequence is accepted, and also one to get the longest prefix of a sequence that the finite state machine accepts. Here is the format, the file format for a finite state machine. First, we have the starting state, Q0. Then the next lines are the transitions. We have at the beginning the state where the transition starts, at the end the state where the transition goes, and in between all the symbols that can go on that. And after the semicolon, we have Q1 and Q2. They are the final states. This was the finite automaton for the integer, very similar for floats and for identifiers. Then a class that creates using an input creates the finite automaton. What I changed is that I also added a semicolon after the starting state so that I can split it. There will also be times when I do a change, a small change to the code and I won't show it. So if something doesn't work, you should check the source code on GitHub because I changed a lot of things on the in the process. So I was saying this class can create a finite automaton from a string input. You can see, you can pause for yourself and see what it does. Back to the Lexer, um, you can see how it tries to extract using the finite automaton. And here is a change to the finite automaton class. I made a mistake. Needed something different in the instructions for else. And if we run a test for mock input, you can see you can print to the output the different tokens. There is a problem for now. As you can see, when there is the expression 3 plus 5, it detects plus 5 as an integer constant and not as an operator. So to fix that, we have to check when extracting numeric constants that before them isn't another integer or constant, because that probably means there should be an operator between them. And now the part that extracts a string. I also wrote a program in a text file, going to run it, created the compiler class that reads the input and calls the lexer function, and here is the output in a file. The next step of the compiling process, as I've said, is syntax analysis. In this process, we will check if the tokens match the grammar of the programming language, or in other words, the rules we described not long ago. Before getting into syntax analysis, I will offer more details about what the grammar does and means. A grammar also describes the rules of a formal language, similar to EBNF. So if we take a EBNF rule from earlier, we can see its grammar counterpart. They are very similar. For the grammar, this is my own notation. The underscore at the beginning means that it's a non-terminal symbol. So if it doesn't have an underscore, it means that it's a terminal symbol. And similar to finite automatons, grammars also have a start symbol. So this is how the grammar looks like. For the implementation, I created a class for a symbol, a class for a production, a class for a context-free grammar, a class that creates a context-free grammar from an input file, and in the compiler I read the grammar from file and I print it out to the output, and you can see some details about it. The parsing process means checking if a sequence matches the rules of a grammar. To achieve that, we will use a parsing algorithm. There are a lot of different ones, but in this video I will show off LL1 parsing, which is a top-down, left-to-right parsing algorithm with one look-ahead symbol that needs a non-ambiguous and non-left recursive grammar. I highly suggest looking at researching more onto this, because it's a bit complicated to explain in a video that is not 4 hours long. This technique uses a parsing table, which makes use of the look-ahead symbol mentioned earlier to determine if a sequence is part of the grammar. The gist of it is that we calculate, when branching off into a different production rule, the first symbol that can appear, and also what symbol can appear after a non-terminal. The tables with this information are called first and follow. Lastly, a class for the analysis table with a map, a class for the table creator, a function that calculates the first one of all non-terminals in a grammar. There are a few rules which I'll not explain right now. You should look them up if you are curious. As I said, first One means the first symbol that can appear at the beginning of the right-hand side of a production. For this test grammar, which is a popular grammar for for expressions, an LL1 grammar for expressions, we can see the last line is the first one of the non-terminals and terminals. Here is a table that shows uh, to be able to check. And the function for follow, I also forgot to mention that epsilon is a symbol that basically means nothing. And we have another symbol, the end marker, which is doesn't appear in the production rule but appears in the follow and is used for the parsing. Follow also has a set of rules that you could look up if you're curious. And we also need a function to determine the first one of a given production. So here I calculate first one, follow one, and for t prime for every production what first one it determines. Now I call the table creator, and for this grammar we can see the analysis, the L1 analysis table, which you can also check on the previous page, see that's correct. And if we try to come back to our original grammar and create analysis table for it, we're going to get a conflict in the table, an error, because our grammar is not an LL1 grammar yet. I mentioned before that it needs to be non-ambiguous and uh, doesn't can't have any left recursion. Um, the problem with an ambiguous grammar is that we use the look ahead symbol to determine if what production rule to use, and if we have two productions, let's say instruction goes into uh, ABC or ADE. Uh, if we have the symbol A in the sequence with only one look ahead symbol, we don't know which of the branches to go, if the first branch or the second branch. So that's where the conflict comes from. So we need to refactor our original grammar for it to be LL1. You can see the changes needed. You can pause and these two grammars are totally equivalent. They're exactly the same. So it's you can look at some of the examples yourself and try to figure out what the rule for factoring is. Then for parsing, we have uh, an abstract syntax tree node class. We're gonna have a tree, and we're gonna need nodes for that. Class with an LL1 parser. It needs a stack, an input stack, and it also has a working stack. It uses the analysis table, and it has the operation to accept if it's both the stacks are at the end marker. To pop, this is quite a long condition. To pop is when the input stack and the working stack both have the same non-terminal at the top of them, so then you can pop the input. If not, we can try to get the next production. If there is no next production, we get an error. Otherwise, using the right side of the next production, we create new nodes and we add them to the working stack. A syntax analyzer class which uses the LL1 parser, creates a stack and analyzes the source code, and a class that writes an abstract syntax data file. For this code, we have this abstract syntax tree. We can see that program goes into the production rule main, open parenthesis, close parenthesis, open brace, instruction list, and at the end is closed brace. And the what's on the same tab level from left to right, they are the right side of the same production. So what if you wanted to write a compiler but not a fully custom one from scratch? Well, more sane people would use some tools like Lex, Flex, and Yak Bison. Lex does the job of a tokenizer, and Flex its upgrade. And Yak does the job of a parser, with Bison being its upgrade. Why? Well, uh, it's very much easier to learn the syntax of how to use these tools than to write a compiler of your own. But obviously, a custom compiler will always be more powerful. You can include whatever features you want. And also at this point of my implementation, there is still a feature for parsing that Yak and Bison have that my implementation does not have. It's called attributed grammars. I'll go over them shortly. So for the rest of this video, I'll be using these. And besides tokenizing and parsing, you will also see generating assembly code and running an executable from this assembly code. So here we have a simple problem. As I said, we will use only a subset of the original programming language. We're going to have reading from input, writing to output, as well as calculating some expressions. This is how a Lex flex file looks like. First, we have some C declarations and headers. Then we can define some regular expressions for integer identifiers for white space. In the next part, whenever we meet one of the things defined above or some other strings, we're gonna execute the code next to them in the parentheses. For now, it only prints to the output. And at the last, the main function which calls this flex function. If we want to run the code, we first have to use the flex. This is in WSL Linux for Windows. This creates this lex.yy.c file. Next, we can compile, so we can see that it's a C file after all, so we can compile it using any C or C++ compiler. I will use this G++, which is a C++ compiler, to create an executable. Then we can use this executable and give it input of the text of the program file. And you can see that it prints every token that it finds, as well as we can see that the integers and identifiers were matched correctly. Now let's take a look at what Yak and Bison are all about. Similar to Flex, we're going to have some declarations at the beginning. We're going to also declare some tokens. And here we have parsing part or syntax analysis part, we can see that it's similar to the grammar, to the way I wrote the grammar with distinct possibilities. An error function as well as calling the parse function of Bison. Yak and Bison are meant to be linked with a stream of tokens. So we're gonna take the input from the flex file. I did some changes to flex. Uh, this Yak Bison file will be compiled into another C file with a. We're gonna import this header. And whenever we match a pattern, instead of printing to the output, we return the token. And to run it, first of all, we're gonna run the Python function. We're gonna run this flex function. We're gonna compile with G++. We're gonna link the lex file with the spec tab C. If I run this parser on the original code, there is no output because it parsed correctly. But if for example, I add a stray semicolon randomly and I run it again, it says that there's a parsing error at line 4 because it doesn't match the rules defined here. So what does Flex and Bison have over my custom compiler right now? Well, basically, Bison can deal with attributed grammars. Whenever it encounters a rule, it can also run some code. I also created a shell file that does all the necessary Bison flex commands and compiling. So now I added this print. So if I compile and run it, we can see declaration input assignment output. In addition, it's called an attributed grammar because we can give each rule an attribute. For now, I declared only one, a string value, which an identifier and an integer token should be given. And we can see that we can access it with a $sign and the digit. The digit represents the position in the rule. The flex file also needs to be modified, so we can initialize the string value. And now if I run this again, we can see that we have an input with the identifier A. And this expression has this identifier and these two integers, and also an output with the identifier A. And what we'll also see later on is that we have the ability to take the attributes of a rule's children and they calculate something based on that. We'll show that later. For the next part about the compiling and running our code, the first problem is working with expressions. When you have an expression just like this, we can't execute the operators in the order they are, because first of all we need to calculate 8 times 2, then we need to calculate 5 times 4, and then we need to add the two of them together. So an easy way to work around that is to transform from infix notation to postfix notation. This is how it looks in postfix. First of all, we have to do a times 2, then 5 times 4, and then we need to add those two results together. So in this C++ file, I have a function that transforms infix to postfix. Now the function is not the the main point of this video. The code will be on GitHub. I won't go into detail about it, but this is what I do for expressions. First of all, the flex file stays mostly the same, I think. There are changes to the Bison file. First of all, we're gonna use this expression utils, as well as some C++ stuff, and a map for symbols. We have a string value attribute and some rules for the attributed grammar. When we meet a declaration, we add to the symbol table the symbol. When you have an identifier equals expression, we transform infix to postfix. I also print the postfix for better understanding, and now I use a function to generate. I will show that soon. And you have a vector code segment that just puts the assembly code. Here I talked about how attributes, the parents can access the attributes of their children. So basically, the string value of factor will be the string value of integer for this rule, the string value of identifier for this rule, and the string value of the expression for this rule with parentheses. An expression can be decomposed using these rules into a sum or you subtract basically the same order of precedence, of operator precedence. So it's a sum of terms. Terms are uh, multiplication of factors, and a factor is either an integer identifier or a expression in parentheses. So this returns uh, at the end of everything, it is an expression, and in this assignment rule, we transform it, as I said, to assembly using this function, which I'll show soon. When we meet an input type, I also forgot to mention that I will use N NASM, so net wide assembler, if you're curious about the assembly syntax. Also, if you don't know about assembly, it's basically very kind of programming language, very close to machine code, so the code that the processor runs. I also use C functions from Microsoft Visual C runtime dynamic link library. Like we have the for an input, we're gonna use the scanf function from, as I said, Microsoft Visual C runtime. For writing to output, we're gonna use the printf function, and also at the end of everything, exit function. Here I have some basic NASM syntax, the declarations, string for input format and output format string. This is a new line. The code segments. So the main point is taking, as I said, we already generate call using the scanf functions and the print functions for this. The main point is calculating expressions. Whenever we call this function with the postfix, we make use of a stack to to calculate. Uh, we see here an example of a postfix notation. We put on the stack a and 2, and when it reaches an operator, it applies it to the last two operands in the stack. Uh, there's a lot of edge cases. The code is very long. It'd be better if you analyzed it on my GitHub. I won't go in detail about every edge case, but mostly what it does, it calculates a factor. So these are the factors: 8 times 2, 5 times 4. Uh, it calculates them and it tries to save them in the EBX register. So for example, this is going to be saved in EBX register. But next up, it needs to calculate 5 times 4. So the EBX register is used up, so it's going to save it in the ECX register. And then it's going to add the results from EBX and ECX. And let's say save it in ECX. And if we had more sums, then it would just calculate another factor, meaning a multiplication of terms, save it in one of EBX or ECX, whichever is free. Then whenever we reach a plus or a minus, then we can take the results from EBX and ECX. Some edge cases about when there's only a uh, single operand in the expression where you directly move the operand in the variable. And I don't remember if there's any interesting cases. You can see some assembly code about moving two registers and phone registers and multiplying. Last of all, the result saved in EIX gets moved to the variable. I also prepared to be able to link the Microsoft Visual C runtime functions. I created a main.c file which calls the start function. The start function was defined here, so it's going to call the piece of assembly code. I prepared the shell script for running. First of all, it compiles into assembly code. Then it compiles the assembly code into an object file, the main.c file meant for linking purposes into another object file. Then it links together the two object files into an executable. For this piece of code, if we run as I said, it prints the postfix. We can read from input, let's say 15, and it writes to output. Like 15 times 2 is 30, plus 5 times 4, that's 30, plus 20, that's 50. So the result is correct. The result is correctly calculated. We can also take a look at the assembly file. Have this file for comparison. how long assembly code needs to be for just a few lines of code. This is kind of reading. Um, you can see that this calculates this factor, saves it in EBX, calculates this factor right here, saves it in ECX, then it loads them in EAX, adds them, saves them in the last register, and then saves them to A. There's some unnecessary code, and unnecessary I mean an instruction like this was not necessary. It's good if there's another sum here, then it's this is correctly saved. Otherwise, this is an optimization. This could be removed, but there's too many edge cases, too many ifs and else's to account for. So there are some assembly structures that are not necessary. So what's to do next? We'll either expand on the Lex, Flex, Yak, Bison variant, or go back to the custom compiler and add the possibility to use an attributed grammar. And before or instead of doing direct code generation, also add the step of intermediate code generation. And that's about it for this monolith of a video. Thank you very much for watching. Honestly, I didn't accomplish as much as I wanted to, but I wanted to get the video out quicker. And maybe I will come back to this project, come back to the custom compiler, add the attributed grammar, intermediate code generation, and everything. And please, if you enjoyed this video, leave a like, a comment for the algorithm, or a subscribe. Anything helps. And see ya.